one thing's for sure, you'll definitely see conditional probability on your end of year exam. And historically, what we've done with conditional probability is look for words like given that to detect whether we've got conditional probability, but it's actually a lot more subtle in 3-4 methods, and it's often implied. So we need to make sure that we're reading these questions carefully. Now, let's just go through a crash course of conditional probability. So we've got two events, A and B here. And what we're after is the probability of A given that B has occurred. And if B has occurred, well, let's get rid of A only and this part outside here. We're not interested in that. We're going to focus our attention on this part here. And we want the probability of A. Well, that's just this part here. How would I describe that? That's just the intersection over the probability of B, because we've got this reduced sample space. Notice that what I've created there is the conditional probability formula. A quick manipulation of that by multiplying both sides by the probability of B will take us to this, the multiplication rule. I've got to admit, I've never really seen that before or officially called the multiplication rule. I wouldn't even think about it, just write that one down or know that one. Actually, that one's even on your formula sheet. So yeah, that's all you need to be aware of is conditional probability can be manipulated to get to do what we want it to do. Okay, it can be seen on a tree diagram. So we've got event A followed by A, and what this is probability of A given A has happened. This one here, probability of B, B given A has happened. So that's what's happened here. To get to this point here, A has occurred, and we're wondering what's the probability of B. Probability of B given A and probability of B given B. So we can see it on tree diagrams. A dice is thrown and an odd number is produced. What's the prob that it's a 5? Well, how many different ways can we get a 5 when we roll a dice? The answer is 1. Okay, now typically the probability of getting a 5 would be 1 in 6, but we're considering the number of ways you can get an odd number, okay, because that's what we know. We know that an odd number is produced. So the number of ways of getting an odd number is 3. So what is the probability of getting a 5 in this instance? It's actually going to be a 1 in 3 chance, not a 1 in 6 chance, because I know that the answer is odd, okay? So again, note that we can think through conditional probability and apply logic to it rather than formulas. Oh, this one's a tough one. Of the 12 students in a school, it was found over the Christmas holidays, 35% had a part-time job on weekends. Let's go let P equal part-time on weekend. And 55% had never had a job. Let, I don't know, U equal unemployed. Never had job. Okay, and what we can do is basically have a look at this as a tree diagram. Okay, because find the probability that a randomly selected student who worked over the Christmas holiday, so we know this, we know that they worked, so they were not unemployed. So unemployed is 55%, never had a job, so that means that's 0.45, and doesn't have a part-time job on the weekend. So if you're unemployed, this branch does not even continue. So we don't consider anything beyond here, because if you're unemployed, you can't work part-time on the weekend. So we're not worried about this branch here. So we're going down here and we're going to note that this is unemployed and either they're going to be working part-time or not part-time. So that's part-time on the weekend is 0.35, not part-time, 0.65. Now, what are we looking at? We're looking at someone who was not unemployed over the Christmas holidays and doesn't have a part-time job, not part-time on the weekend. So that's going to be probability of that doesn't have a part-time job on the weekend, given that they were not unemployed over the holidays. Now we can use the conditional probability formula, or we can note that it's actually just going to be 0.65, because that's all this is. This is the probability of not being part-time on the weekends, given that they weren't unemployed over the holidays. So the answer should be 0.65, but let's just run it through the formula and check out how this works. P and not P and not U over the probability of not U. Okay, P and U means we're going to do 0.45 times 0.65 all over that, which is 0.45. Yep, for sure. They cancel out, leaving us with that, or as you can see here, I quickly worked out on my calculator, is 13 on 20 as a fraction. Right, in a certain town, the prob that it rains on any Monday is 0.21. If it rains on Monday, then the prob that it rains on Tuesday is 0.83. All right, now this one here again lends itself to a tree diagram because either it rains or it doesn't rain, and this is Monday. So probably that it rains on Monday is 0.21, so that means 0.79. And then Tuesday, same deal, it can either rain or not rain, rain or not rain. If it rains on Monday, then the prob that it rains on Tuesday is 0.83. So rain on Monday, rain on Tuesday, 0.83, which means that's 0.17. If it doesn't rain on Monday, so not rain on Monday, probability of rain on Tuesday is 0.3, 0.7. What's the chance that it rains on both Monday and Tuesday? So we're going to have rain followed by rain. So this one here is going to be 0.21 times 0.83, which is that. Okay, what about for any given, find the probability that it rains on Tuesday. All right, so rain on Tuesday means rain and rain, or not rain and rain. So that's what we're after, these two conditions. Now we've already worked out that one. That's going to be 1743 over 10,000. These two here, we're going to multiply them out. So rain and, not rain and rain. So that's 0.79 multiplied by 0.3, which is that. And then what we'll do is we'll just add them together. So it's that plus whatever's in the answer slot. Okay, so this one here is going to be 1743 over 10,000 plus 237 over 1,000, which is equal to 4113 over 10,000. Easily express that as a decimal, 0.4113. Okay, so on to independent events. Flipping hell, Finch's unwanted cup record. Australia's skipper will be looking to end a streak of 7 consecutive defeats at the coin toss tonight against Bangladesh. What will Finch do? Your answer should be, who cares? Why? Because each coin toss is independent of the last. The fact that he's had 7 consecutive defeats does not mean a thing. Okay, that every time you go to a coin toss, it doesn't matter what's happened in the past. The coin does not have a memory. The coin doesn't know that Finch has just lost 6 consecutive coin tosses. Okay, so it will come up as either a head or a tail. This is a redundant headline. Makes good news though. And even though we know that each toss is independent of the last in roulette, this is the results of one particular table that I saw on the internet, okay, where the roulette wheel came up with 19, not once, twice, 3, 4, 5, 6, 7 times in a row. Red 19 came up 7 times in a row, followed by 2 lots of the 20. Amazing. Okay, so someone, you might think something is going on here, but actually this result here would be exactly the same as if 19, 20, 36, 45, 60, whatever the numbers are. I don't even know what the numbers are in roulette, but it doesn't matter. These things here, again, do not mean a thing at the casino. They only help serve or to play on what we call the gambler's fallacy. okay, that the roulette wheel or the coin toss has a mind of its own. So two events are independent if the probability of A given B is the same as the probability of A. That is, I give you a little bit more information about what's happened, but it's still just the probability of the event happening. So in the case of a roulette table, if I said to you, this is the history of the roulette table, we got 7 19s followed by 20. What do you think will happen next? You just go, whatever it is, there's a 1 in whatever it is chance of my number coming up. Or if I told you that Aaron Finch, is it Aaron Finch? Yeah, I think it's Aaron Finch, has lost 7 consecutive defeats in the coin toss, what do you think his chances are tonight? You'd be like, yeah, 1 in 2. All right, and that means that if probability of A intersect B is equal to the probability of A, okay, so we can actually change that formula there to write it as probability of A intersect B over the probability of B. That's the conditional prob formula, equals probability of A, and then transpose it. So probability of A intersect B equals probability of A times probability of B. Right, so that's just in another version of this formula here. Common misconception is that just because two events are independent, they're mutually exclusive, but actually that's not the case. For mutually exclusive events, the intersection is 0. Okay, and when this is the case, you can see how it might cause problems, which is the null set will equal the probability of A times the probability of B. So for this to be the case, either event A or B would have to be the null set. All right, and why would B be looking at independent events where one event is the null set, i.e. it's got nothing in it, okay? So basically, and to hark back on what I was alluding to earlier, independence and mutual exclusivity are not one and the same thing. They're completely different, okay? Okay, so I've said here, in many situations, it's difficult to see whether events are independent or not, and you need to run one of the following tests. Okay, the probability that Judy remembers to do her homework is 0.7, so probability Judy is 0.7. Probability that Jenny remembers to do her homework is 0.4, less reliable, Jenny. If these two events are independent, so they're telling us that they're independent, then what's the probability that they both will do their homework? So we want to work out the probability of Judy and Jenny doing her homework, and because they're independent events, that it will equal probability of Judy multiplied by probability of Jenny, just using the formula. Judy will do her homework, so we want this probability of Judy and not Jenny. Right, now probably the easiest way to do this one here is to just quickly knock together a table. So we've got Jenny, Jenny not, sorry, that's Judy, and Jenny not. That's going to be 1. So the probability that Judy remembers is 0.7, Jenny 0.4, and Judy and Jenny, because they're independent events, we can multiply those two together to get that. That's 0.6. And what do I want? I want Judy and not Jenny. I want this one here. So that's going to be 0.7, take away 0.28, 0.4, 0.42. So Judy will do her homework, but Jenny forgets is going to be Judy and not Jenny. So yeah, I've just used the table to get the relevant information there. All right, so this is one where you need to test independence. Okay, so this one here, we've got a dice being rolled and the following events occur. So A, the first roll shows a 4. So probability of A, the first roll shows a 4, is of course 1 in 6. Right, there they are there. The second roll shows a 4. Well, the second roll shows a 4. Okay, is this one here? That's just going to be 1 in 6. Some of the numbers showing is at least 10. At least 10 means 10 or more. That's those ones, which is 6 in 36 or 1 in 6. All right, are A and B independent events? So probability of A times probability of B equals probability of A and B. So that's what I'm going to do. I'm going to run the test. So that's 1 in 6 times 1 in 6. Actually, let's think about what A and B are. First roll shows a 4 and second roll shows a 4. Of course, they should be independent of each other because that would be like each roll is independent of the last. So A and B, first roll and second roll is a 4. That's 4, 4. That's a 1 in 36 chance. So that means that that's 1 6 times 1 6 is 1 over 36 equals 136. Therefore, they are independent. What about A and C? All right, so this one here is first roll shows a 4. Sum of the numbers showing is at least 10. Okay, now do you think that the first roll showing a 4 has some impact on the numbers showing up is at least 10? All right, so if this is what we were looking at, sum of the numbers showing is at least 10. If I said to you, would you be interested in knowing what the first roll is or whether the first roll is a 4 or not? Would you be interested in that? I bet you would say, yeah, I probably would, because like if it's a 4, 4 is pretty high, so the sum of the numbers showing is at least 10 is, yeah. So I would say that there's some dependence between these. Getting at least a 10 would have be impacted by the first roll being 4. Let's just check it out. So we've got the probability of A times the probability of C equals probability of A and C. Probability of A is 1 in 6. Probability of C is 1 in 6 in 36, which is 1 in 6. Probability of A and C, that's first roll shows a 4 and sum is at least 10. All right, so first roll shows a 4, sum is at least 10. So this is the only one with first roll shows a 4. That's 1 in 36. Now, what's 1 6 times 1 6? That's 1 in 36 is the same as 1 in 36. Therefore, these events are independent of each other. That means the first roll showing a 4 has no impact on the sum of the numbers showing is at least 10. Okay, so they're independent of each other. Now, that's a weird one, but there's no obvious physical independence. One seems to depend on each other, but they're mathematically independent. Okay. Now, if you ask me to whether I could do that in my head, there's no way I could do it. I would check the test on that one. Right. So your practice time now will involve you working through those particular questions there from 30B.